Bona tarda, gràcies per estar aquí i benvinguts a la primera d'una sèrie de xerrades que l'Escola de Camins, tenim la directora per aquí, que l'Escola de Camins està organitzant amb ocasió del seu 50 aniversari i aquesta vegada hem aprofitat de l'ocasió que a la reunió del Consell Científic del CIMNE hi participava la professora Karen Willcox i ha tingut a bé oferir aquesta xerrada. Welcome everybody. I was just addressing to the locals. So we are extremely happy to open this series of conferences in occasion of the 50th anniversary of the Civil School of Engineering, l'Escola de Camins, and taking the occasion of having Karen Willcox with us in the Scientific Advisory Council of CIMNE, and then she was very kind to accept to give this talk. She's going to discuss a concept which is familiar for some of us, but I believe it deserves dissemination, which is digital twins, and we'll look forward to your speech. Thank you very much.
All right. Well, thank you very much, Pedro. So I would like to thank to Pedro Diaz and to Javier Bonet for hosting me here. It's wonderful to be here in Barcelona and actually to be enjoying the wintry weather that's just like it is in Texas, beautiful blue skies. So a very big congratulations to the School of Civil Engineering on 50 years. This is an amazing accomplishment. And in fact, the institute that I direct back in Texas, the Odin Institute for Computational Engineering Sciences, some of you may know it as ICES, we are also celebrating 50 years this year. And so I think it's really important that we take a minute to think about what the world was like in 1973 when the School of Civil Engineering here was founded, when the Odin Institute was founded, and think about the challenges the world was facing. And just to think about whether our founders could have imagined 2023 and the kinds of things that we'd be waking up to read in the news. And while many of the challenges are the same, so much has changed. It's also really wonderful to be here today. It was my first visit to CIMNE, if I'm saying it close to right, which, where is Eugenio? Right there, which is right up there with the Odin Institute in terms of having such an incredible global presence and reputation as being one of the amazing places where computational mechanics has really been founded and advanced over the years. And so it's really an honor to join the Scientific Advisory Council and to visit CIMNE. And I really enjoyed today getting to see some of the things that are going on. So tonight I am going to talk, as Pedro said, about digital twins. So I was instructed to give a public lecture, and I asked twice, when we say public, do we mean the public or do we mean all engineers and scientists? So I'm actually curious, who in here is an engineer? Oh, look at that. That's great. So who here is not an engineer? Oh, good. We've got some, including my 8-year-old daughter, who's waving her hand back there. So hopefully for the engineers, there'll be a little bit of hints at the technical work that we do that will keep you excited. But in the interest of really giving a public lecture aimed at dissemination, because one thing that I think we engineers, and now I'm speaking to 95% of you in the room, as engineers, we have not and do not do a good enough job of explaining to the world why what we do is so important. And again, if you think of 50 years of civil engineering, can you imagine what the city of Barcelona would look like without those 50 years of civil engineering? Yet somehow the decision makers, the politicians in our society think that AI and computer science has brought the revolution of computing to society, which is true in some ways. But again, we as engineers know what a long history we have and how much that's contributed to the world around us. So today's talk will be sort of aimed at that audience, which is understanding what is a digital twin and why is it important and why is it something that really needs continued investment in engineering, mathematics, computational science, computational mechanics, high-performance computing, and everything that goes with it. Okay, so as you can tell, I already like to move around and use my hands in the talk. I like to also be near the slides. I'm going to try very hard not to fall off the stage as I come here near the screen, the way it's positioned. All right, so we'll start right out. What is a digital twin? And I expect with the number of engineers in the audience, pretty much everybody here knows has heard of a digital twin and has perhaps their own definition. But nonetheless, let's think about what really is a digital twin. What do we mean when we say that phrase? So we're going to first start in the past, and some of you may have heard this story. We're going to go back to the 1960s and the 1970s to the Apollo program in the US, where was an incredibly exciting time for space. And in fact, that's one of the reasons I became an engineer, is because growing up, I was inspired by what had happened with Apollo. And in fact, I wanted to be an astronaut, but I became an engineer instead. So back in the Apollo program, when NASA launched spacecraft into space, at the same time, they would keep a simulator on the ground in Houston. And this wasn't a digital simulator. We didn't really have the digital tools at that scale yet, but it was a physical simulator. And the idea is that as the physical spacecraft was conducting its mission, the simulator on the ground in Houston would follow along. And of course, this was so important in Apollo 13, which we know the story of Apollo 13 in large part thanks to Hollywood and Tom Hanks. We know the story. There was an accident on board. The spacecraft was badly damaged. It became crippled. It became stranded up in space. And so the story goes that NASA were able to take the data from the sensors and the observations on board the physical spacecraft stuck up in space, take the data, feed it into the simulator on the ground in Houston, adapt that simulator so that now it reflected the conditions of the damaged spacecraft, and then use the simulator to play the what-ifs and run the scenarios, ultimately drive the decisions that brought the astronauts back home safely. So again, this is just a little over 50 years ago, this idea of simulation and taking the data and adapting the simulator to drive decisions. Let's come to today and let's think about an entirely different set of applications. So in particular, high-grade gliomas. So what is that? This is a kind of, a particular kind of brain cancer. And again, if we think about today, for a patient who has been diagnosed, who has one of these brain cancers, what does treatment look like? Treatment looks like something called the standard of care that you see here, where after surgery, there's an image, and we're going to count that as day 0. At day 20, there's another image, and then the radiotherapy, in this example, treatment planning starts. And the radiotherapy treatment planning says that for 1, 2, 3, 4, 5, 6 weeks, the patient will receive 2 grays per day of radiation. That's the dosage of radiation on Monday, Tuesday, Wednesday, Thursday, and Friday. So 2 grays per day for 5 days a week, then the weekends off, and repeated for 6 weeks. And that's, again, the standard regimen. That's what's called the standard of care. And then out at day 152, we would see another an assessment and then eventually an image taken. So that's today. Now I want you to think about a future that's not here yet, where rather than every patient coming in receiving this standard of care, instead it's possible to take the images, to construct a patient-specific plan that says, and in the example that we're showing here, in week 1, we'll give everybody the same treatment, 2 grays per day for 5 days, but then starting in week 2, we'll optimize the treatment according to what we have learned, according to information that we've learned about you. And of course, with all the engineers in the room, I don't have to probably lay out the advantages of what might happen if we could think about optimizing treatments on a patient-by-patient basis. So what do these 2 things have in common? 2 really different applications. the brain tumors, and I'll get to it a little later on, but I do just want to point out the image credit there. My group is doing some work with the Center for Computational Oncology, which is also a part of the Odin Institute, my colleague Tom Yankelov. So we've got the brain cancer and the Apollo spacecraft, and especially the Apollo 13 example. What do these have in common? So what's in common here is that there's a need to drive decisions. And those are decisions where people's lives are at stake. And by the way, this is what we do as engineers. We drive decision-making where people's lives are at stake. How can good decisions be made? It's through prediction. Again, this is what we do as engineers. We don't just collect piles of data and learn about what's happened in the past. We make predictions about the future. How do we make predictions? We do that with models. Models that encode the governing laws of nature, conservation of mass, momentum, and energy, or the biological and chemical balances that might be in the brain. And we combine those models with data, and in these two examples, data that are collected about specific objects or specific people undergoing dynamically changing situations. And so putting those, sort of all those ingredients together, taking models, not just the models that are in the textbook and are coded up on a supercomputer, but models that are collecting data from a patient or collecting data from a spacecraft, and collecting that data time and time and time again so that the models now can dynamically evolve through the mathematical process of data assimilation to drive these predictions and ultimately drive decisions. And so this, to me, this is what a digital twin is. It's putting all these pieces together. Take your favorite physical system, whether it's a brain, an airplane, or maybe something in the natural world. So the picture here of the Antarctic ice sheet. Take a virtual representation. And sorry, I'm just noticing that the slides are a little hanging off the screen, but that's all right. We've got the important parts here. So physical system, take a virtual representation of that physical system. And again, what is a virtual representation? It's some kind of a mathematical model encoded in some kind of a numerical model. And then to think about the connections, the interactions between the physical world and our virtual representation. So the flow from physical to virtual, this is where we take data or make observations about the physical system and feed that data, feed those observations into the virtual representation to calibrate it or to update it. Mathematically, that is classically an inverse problem or a data assimilation problem, may involve sensor fusion, may involve model adaptation. And then the feedback flow coming the other way from the virtual representation to the physical system. This is where now we take our virtual representation, our model that has assimilated data, that has been adapted, and use it to affect the physical world. And that effect might be through control, so through some kind of an automated control system. It could be in terms of providing predictions for humans to make the decisions. That was the Apollo example. Right? It wasn't automated control. It was making predictions for human decision support. It could also be that the virtual representation is used to guide sensor steering or experimental design, so to make decisions about what additional information to collect from the physical system. So for example, if we think of the cancer patient, this flow here might include optimizing treatment, but it might also include decisions like when to collect another image, when to go in for another MRI, when to run another test. So physical system, virtual representation, and then these two feedback flows from physical to virtual and virtual to physical. One last important piece, which is the extremely important role of validation, verification, and uncertainty quantification, which is it's not enough to just throw these virtual representations up to to adapt them from data without giving careful care to what's going on with the models and how much can we trust those predictions that are ultimately going to drive decisions. So back to the question that was on the first slide, what is a digital twin? When I think of a digital twin, I think of all of this. I think in many cases we see digital twins and we see just this part. People will sometimes call something a digital twin, and really it's just a virtual representation of the system. I think the real power of a digital twin, or really what is a digital twin, it's this virtual representation with these bidirectional feedback flows so that the virtual and the physical have this interacting relationship between them. And again, really can't overemphasize the importance here. And by the way, this again is something we know as engineers. I sometimes wonder if the incredible pace at which AI is developing, let's say in contrast to how long it's taken us to develop incredibly powerful tools like the finite element method, is because AI is done without these things having to be essential. Yeah, we can laugh, but it's quite, people talk about the pace of acceleration, Eugenio, where you said, I keep losing you. How much faster could you have gone if you didn't actually have to validate any of your numerical results, if you didn't need mathematical theorems, if you didn't need proofs of convergence? You could have gone a lot faster, right? Especially if you only had to be right 90% of the time. So injecting these notions into digital twins is so incredibly important, and if we don't do this, I think we'll be in real trouble. All right, so this notion of a digital twin, I gave the Apollo example. I said that wasn't really a digital twin, it was a physical simulator. But the term digital twin itself does come from aerospace engineering. Again, NASA, back in 2010, the term was coined in actually an internal NASA report. There was a couple of AIAA, American Institute of Aeronautics and Astronautics papers right after that, that put forward the concept of a digital twin for structural health monitoring of aircraft wings. So again, roots in aerospace engineering. And today, if we look at the term digital twins, we see really, again, this incredible potential to revolutionize decision-making across so many areas. The examples that are shown here, these are all things going on in the Odin Institute. So here, 3 examples from engineering. So I'm doing work with digital twins for unmanned aerial vehicles to help drive operational decision-making. My colleague Omar Gattas is doing work with digital twins for advanced manufacturing processes. And then Marie Vajar, digital twins of space, as we start to grapple with the incredible complexity of what's going on in space in terms of space debris and incredible clutter. And again, a need to map out and ultimately make decisions about how we manage space. If we think about the natural world, of course, climate change and climate adaptation are on many people's minds. So thinking about digital twins as a way to build these living models that can evolve as our natural world is evolving, and again, using those digital twins to drive decision-making. So again, Omar here with a full-scale model of the Antarctic continent, the Antarctic ice sheets, and then Patrick Heimbach, who does a lot of work with really high-performance models of ocean ice sheet interactions. And that's it's maybe not displaying too well, but a beautiful visualization of a simulation of Greenland. And then, as I've already alluded to, I think the potential of digital twins in medicine is just tremendous. And it's one actually where I do think the public can really start to appreciate how you bring all these different ingredients together, how you bring the models and the data together to drive patient-specific models and really lead to decision-making that has improved outcomes for patients. So really exciting time. All right, so this is wonderful, and sometimes talking to non-experts, they'll say, oh, this is so great, Karen. You know, where should I tell my doctor to go? How do I get my digital twin? It's such a great promise, and we can all imagine, whether it's our favorite engineering system or whether it's a medical application, we can all imagine what we would do with our digital twin if we had it. But the reality is that for many systems, we're just not there yet. So in the next part, I wanted to talk a little bit about why it's very difficult and why don't we have digital twins of all these things available to us today. So the first thing that I think is important is that when I talk about all these things, I talk about models and data and the connection between the physical and the virtual. But when you start to think about a digital twin, I think for many people, they go immediately to this notion of it's big data. And in fact, we were talking with some reporters this morning, and one of them said, oh, digital twin, this is big data, right? So we think of the data as being the core of the digital twin. And what goes around there is some kind of numerical model. And if it is a big, massive data set, and you're in the year 2023, the chances are that numerical model probably involves a deep neural network of some kind. It could be a more classical statistical model, but it's quite likely a machine learning model. And then push that one too many times. Around that numerical model, you might have a layer of analytics, which ultimately then you would use to drive decision making. So this is one way, for sure, you could think about a digital twin. And I think if you were to go out into industry and look for some of the most successful today versions of digital twins, and the ones that come to mind are, for example, the digital twins of aircraft engines. Probably many of you have read news articles about the digital twins that are used for predictive maintenance of aircraft engines. I think those are digital twins that really fit this model. There is a ton of data collected from an aircraft engine every time it flies. And so first of all, it truly is big data. There's a ton of data. Second, the decisions that you have to make about predictive maintenance, these are decisions that are relatively simple decisions, and the decisions fall within the realm of the data that you've collected, right? You're collecting data from across your fleet of engines, and you have to make decisions about when and how to do maintenance. Again, this is a decision space where it really falls within your data. So we'll keep this one in mind because we're going to come back to it. This certainly is one way to think about a digital twin, and I think applications where this is the case, where you have a ton of data, and the data describe the decisions you need to make, this is a way to architect the digital twin. But for many, many, many applications, the story is not that simple. And the story's not that simple because, remember, go back to the beginning, we said, what is it that we need to be able to do to have these digital twins be useful? We have to predict the future. We have to make predictions about conditions for which we may have no data. And we may not have any data because we may not want our system to be getting into these particular conditions. So why is it so hard to make predictions for complex systems? First off, we're talking about complex physical phenomena, multi-physics, multi-scale, and again, we could get into all kinds of technical details about why that makes it difficult to predict. And by the way, the conditions that are most critical to predict for decision making, particularly in engineering, are ones associated with some kind of failure, which by definition is some of the more extreme behavior that a system might see. So just the complexity of these physical phenomena make it difficult. Next, high dimensionality. As I start talking about building a digital twin of something as complex, well, certainly as complex as a human or a human organ, but think of your favorite engineering system, we're going to be talking about parameters spaces, so things that can change in the system of high dimensionality, hundreds of thousands, millions, maybe even billions of different parameters that you could think about in the system. We're going to have real computational constraints. We talked about the importance of the updating of the digital twin. If that updating has to take place in real time or near real time, so if you have an airplane flying around and you need to update the digital twin while it's flying, then that puts all kinds of computational constraints in terms of what computing power you might have on board the aircraft or what communications you might or might not have and how much time you have to do the updating and make these predictions. The bottom one, verification, validation, uncertainty, quantification, I think I already made that point. That's so important, it makes the problem hard. So let's go to the fourth one, which is limited data. And again, we looked at the looked at the conceptual view of a digital twin with data as a core. And yes, we do live in the era of big data, but nonetheless, there are so many problems for which the data we have are actually very limited. They may be big as measured in bytes, but the data are very, very limited compared to the process we're trying to characterize. And I have a couple pictures here as examples, if you can see them. So the picture up here on the top, on the two are there on the right, that's the unmanned aerial vehicle that I have in my research group. And I sometimes have very interesting conversations with the medical people because they say, and more than one has said to me, Karen, you're so lucky that you're an engineer because engineers can measure whatever they want. So I don't know if there are any experimentalists here today, but we should all know that as engineers, we can almost never measure what it is we want to know. And in the unmanned aerial vehicle that we fly, you can see that mess of strain gauges on the surface. We don't want to measure the strain on the surface of the aircraft. We want to know what the health of the structure is inside. Just like in medicine, we are limited to taking measurements from the outside, trying to guess what's going on inside. Those measurements are noisy, they're indirect, and what's more, they are sparse because every sensor that we put on board the aircraft adds weight, it adds cost, and it consumes power. And so that's just one example, but in so many engineering systems, I do also a lot of work on rocket engines with the US Air Force. There, it is very, very hard to get experimental measurements. So the data may be big in size, but they're very, very limited. And of course, when we think about the medical applications, again, we have the problem of the indirect, noisy measurements. There's a really interesting added complication in medicine, which is the measurements are very sparse in time. So when you go back to the example of a cancer patient, depending on the type of cancer, you may be getting an image once a month or even once every 3 months. And again, this may be big data, but can you imagine trying to characterize the dynamic properties of an evolving tumor with samples once every 3 months? Right? The data are never going to be enough on their own for these kinds of examples. We need to fill in those gaps in the data, and that's where the physics come in. This is where the predictive power, the interpretability, and the domain knowledge of our physical models comes in, and these have to be a part of the digital twin. So for all these kinds of problems, and by the way, climate would be another one. If you just think about how many observations we could possibly take of the ocean, and it's just not feasible to think about sensing the ocean or our atmosphere at the scale that would be needed to rely only on the data. So for these kinds of examples, we need to change the conceptualization of a digital twin. Instead of having data at the core, we really need to think about a mathematical model at the core. And this mathematical model is the model that encompasses what we know about these systems, the physics, the governing laws of nature. It could be empirical models. It could be first principles models. It could be mechanistic models. Perhaps most likely, it's going to be some combination of all of those things, knowing that there are some parts of our systems that we understand well and others that we really don't. Then that mathematical model is encapsulated with a numerical model. And again, the numerical model may be a machine learning model. For many of the examples that I've given, this numerical model will be something like the finite element method or one of the very powerful methods of computational mechanics that lets us solve incredibly difficult problems that describe the physical, the spatial and temporal evolution of these physical processes. So a numerical model. Then the data still play an incredibly important role because remember, our digital twin needs that interaction between the physical and the virtual. The data now come in through the lens of these models as an inverse problem, as a data assimilation problem, and then all of it together drives decision making. So 2 views of a digital twin. both are valid, both have their place, but I think it's really, really important to think intentionally about the system that you're building a digital twin of, and to think about how well you can model it, how much data you really have, and how you put these ingredients together in a way that's meaningful. And I'm sure all of you could be thinking about maybe even ways you could change this schematic and mix it up even more. All right, so let's see, in the last part of the talk, without getting into too many technical details, I wanted to give you just a couple of highlights of some of the work in my group and how we're approaching digital twins and how we try to address some of these challenges. And in particular, I want to show you how we've been developing a probabilistic graphical model as a way to really think about a foundation for digital twins. And so what is a probabilistic graphical model? You'll see it only very superficially, but just to maybe say that probabilistic graphical models have got a lot of use in robotics. And in fact, it's really the field of robotics where we drew a lot of inspiration from some of the work. And if we think about other fields that have long, I don't know how long, but have considered this interaction between the physical and the virtual with this bidirectional feedback loop of updating models and using models to drive decision making, then robotics is a really great example of that. Of course, in robotics, the kinds of models traditionally have been a little simpler than the kinds of models that we're thinking about as engineers or in medicine. But I think it's a really powerful way to abstract and think about digital twins. So what does this mean? This means now we need a language, we need a mathematical language to think about our digital twin. And we do that by abstracting it in this way, where, and I'm going to give you some examples here from an aircraft, where we think about the physical state of the system. What is it that you want to be able to track? And what are all the things you wish you could know, but probably can't? What data do you have? What observational data do you have? So you might have sensors deployed on the aircraft wing, but you might also have inspections or flight logs or data recorders from the flights. You could have all different kinds of data available to you. And what kinds of decisions can you make? We call them control inputs. What kinds of actions or decisions can you take that will affect your physical asset? So that could be controls while the airplane's flying. That could be deflecting the control surfaces. But it could also be decisions that say, go and do a maintenance, or go and do an extra inspection, or go and install a new sensor on board the aircraft. So these things all live in the physical world, the physical state of the in this case, aircraft, the observational data we can collect, and the actions or the decisions we can make. In our digital space now, we think about the digital state. How are we going to represent this complex system in the digital world? What kinds of parameters will I use to describe it? What kinds of models do I have? What do I know? What governing laws do I have? So the digital state really encompassing my now modeling decision on how to represent this aircraft in the digital world. I can define quantities of interest. What are the quantities? What are the things that I really care about predicting? Because those are the things that are going to drive decisions. And in my aircraft example, that might be a maximum stress on the wing because I want to know whether the wing's going to break or not. Or it could be something related to the health or the safety of the aircraft. So the quantities that I really, really want to get right. And then finally, the reward. How do I know what's good? How do I make decisions? I need a way to measure whether a decision is good or not. And so a reward might encompass performance, environmental impact, cost, safety, all the ways in which you would bring in all the ways in which you would measure the quality of a decision. So we formally identify these, and these 6 quantities give us a mathematical language for us now to start thinking about digital twins. And we take these quantities and we use them to construct a probabilistic graphical model. And I've spared you the next step because that's a little bit more technical. But just like it sounds, it's a graph. It's mathematically a graph that expresses all the relationships between these different parts of the digital twin system and also encodes all the information, all the models that we bring. And when we have this probabilistic graphical model, we can now start to do things like you see depicted in this picture here, which is taking my unmanned aerial vehicle, and you saw a photo of it a few slides ago. So I've got this UAV that we designed and built, and it sits in my actually it sits in the garage of my house in Austin, Texas. We can start with a baseline model, which is a generic model of all the UAVs that kind of look like that. We can collect data. We can do, we can take measurements. We can test the UAV, and we can calibrate the geometry, the material properties, mass, damping, all these characteristics of my aircraft, so that once we get to this point here, we have now a digital twin, and that our models have assimilated all the data we've collected, and now they represent my personal unmanned aerial vehicle, which might be different to your one, which might be different to somebody else's, so they've been personalized. And now we have this personalized model. We can use it to do things like now when the UAV is flying, we can keep collecting data from those strain gauges that you saw on the wing. And if, for example, the aircraft is flying around and it gets damaged, we could update the digital twin in real time and use that to drive decision-making for the aircraft. So here's just a few more pictures of the aircraft and various pieces of it set up in the lab. I should say we designed and built this aircraft together with Aurora Flight Sciences. That's back when I was still at MIT in Boston. So this is the aircraft at its first flight in Massachusetts. Then the aircraft moved with me to Texas, and we were getting ready to do more flight testing in Texas, and then the pandemic hit, and all labs and everything on campus got closed down, so the wing had to come home. And so now you can see it there. That's again in my garage in Austin, and I had to put my middle schooler son to work collecting. He's there collecting strain data from an oscilloscope. So I'm sure, especially to the students here, when the pandemic hit, we all had to make kind of unusual plans on how to get our research done. Actually, I'm not sure I sort of said that while being recorded, because I don't know if it was legal to do those tests. That's okay, it's done now. I had a PhD student who needed to graduate. Okay, so there's the physical hardware. Again, without going into the technical details, I talked a lot about the models and encoding the physical principles in models. One of the things that's really important for digital twins is that the models are computationally efficient, in part because you may need to run them in real time, but also because all these things I've talked about, data assimilation, decision-making, uncertainty quantification, they require the models to be run many times, thousands and thousands of times. And so as powerful as finite element models are, and you can see here a little bit of picture of the finite element we build, and we build it to really try to mimic what goes on in the real wing. You can see here, just going off the bottom of the slide, it takes about a minute to run one finite element analysis, which is pretty amazing in itself, but this is too slow for a digital twin. We want to be able to run these models very rapidly. And so one of the other pieces that we work on is the notion of a reduced order model. So this is starting with the finite element model, which has all the physics we want to capture, but now coming up with a simpler, faster surrogate model that gives more or less the same answer, but does it much faster, and in this case gives us more than 1,000x speed up, so the reduced order model will run in a fraction of a second. And again, to really emphasize that these reduced order models are embedding the physics and are giving us an approximation, but doing it in a way where we really know how good the answer is. That validation, that uncertainty quantification is very rigorously embedded in those reduced order models. And that reduced order modeling work is together with Axelos. All right, so we can put all this together. We're losing just a little bit of the slide, but I think you can still see what's going on. So here's a simulation. We've got the aircraft and it's flying here on this reddish flight path. The aggressive flight path is shorter, so you get there faster, burn less fuel. But when you take a tighter turn around the corner, you put more load on the wing. So the more aggressive the flight path, it's preferred, but it puts more load. So what are we modeling here? The aircraft is flying. Right about here, it incurs some damage. We're going to see some damage pop up here on the panels and the wing. And you can see up there on the right that we're collecting strain data. And as the damage is getting worse, the digital twin is eventually realizing your damage has gotten to the point where you no longer can sustain this tight turn. You need to switch over to the conservative flight path. So again, just sort of a simple illustration, but fast forward in future to maybe a future where we have Amazon deliveries with drones, or we have unmanned vehicles. Maybe we have unmanned taxis. Instead of dealing with the Barcelona traffic, we're able to fly to where we need to go. I don't know how many years that is away. These autonomous vehicles are going to need these kinds of real-time health monitoring in order to be safe. And I think digital twin is really a way that we can think about making that happen. Okay, maybe in just the last few minutes, I want to talk a little bit about the work we've been doing with the oncologists. And I want to show you this because you'll see that, you remember I said that we need some mathematical language to think about a digital twin. And the idea is that this language could let me think about the digital twin of an aircraft and then take the same language and use it to think about a digital twin of a cancer patient. And while the physics are very different, all the concepts that I've talked about are very similar. And in fact, you would probably be quite struck, I've been quite struck by the analogies between health monitoring of aircraft wings and health monitoring of humans. There's incredible analogies in terms of the data, the models, the predictions, the decisions we need to make. It's actually quite beautiful. So in our abstraction of a now cancer patient twin system, again, we can think about the physical state. Instead of the geometry of the aircraft, it might be the anatomy of the human brain and the skull. We can think about the data that can be collected. And again, just like in engineering, there's all different modalities of data that are available. And we can think about the decisions that need to be made. And as I said earlier, those decisions are not just treatment, but also decisions to do additional imaging or to collect additional data. And just like in the aircraft example, we need to think very intentionally about how we represent the system in the digital world. So our mechanistic models for tumor dynamics or tumor mechanics, and by the way, many of the governing equations are also in common. We need to think about quantities of interest. What is it that, especially now a doctor, because we may be working, the digital twin is likely working with a human decision maker, with a doctor. What are the quantities of interest that a doctor wants to see predicted in order to drive decisions? And reward, how do you evaluate whether a decision is good? It's some combination of patient outcomes with adverse effects, short-term versus long-term costs, how intrusive tests might be, and so on. So many factors into the rewards. And again, just like in the aircraft system, we can think about following exactly the same process where we start off with a baseline model, a sort of a generic model of maybe a brain, using the imaging and all the advances that have been made in imaging. You can start now to calibrate the initial conditions of a tumor, calibrating the physiology of the tumor, calibrating the way in which the patient responds to radiation. Even if we had identical anatomies and the same initial tumors, our bodies would likely respond very, very differently to the radiation. And then coming up with this personalized digital twin that could then be used to drive optimal decisions on those radiotherapy treatments. And you saw this picture already right in the beginning, but this is really where we're going, is trying to optimize the radiotherapy regimens, and this is the setup for the first study that we've done. So I did want to show you, I know these probably break the rules of being too technical for a truly public lecture, but if I walk you through them, I think this really highlights both a challenge and an opportunity for digital twins in the medical space. I think this is also true in climate sciences, and maybe a little bit less so in engineering. So what are we looking at here? We are looking at 4 key parameters. These are 4 physical parameters: proliferation rate, carrying capacity, radiosensitivity parameter, and initial tumor burdens. These are parameters that show up in the models. And the spread here is the uncertainty. So what this says, and by the way, this is based on population data. If a doctor or a biomedical engineer or a modeler were to come in and to create a model of my brain with a tumor in it, they wouldn't really know where to set these parameters, and it could be pretty much anywhere in this range. And so you look at that and you say, well, I don't know, is that a lot of uncertainty? If we take this uncertainty and we push this uncertainty forward through the models, and we compute with the models tumor cell count versus time, and this axis here is in days, then the dark line here is the mean, that's the prediction we make, and the band is the uncertainty. So you can see here, this is the tumor cell count growing. You can see this is where radiation therapy starts, drops, and it's dropping, and it's dropping, and it continues to drop, and then it stays at bay, and then eventually the tumor cell starts to grow again. So again, the dark line is the prediction, but the band is the uncertainty, and you can see that basically is very uncertain. They really have very little idea about what happens out here past the end of radiotherapy. Okay, so this is where a digital twin could make a huge difference, because what are we going to do? We're going to come in, and now these are virtual patients. So with our collaborators, we have the actual patient population data. These patients are virtual patients. They're sort of made-up patients. The patient can come in and be imaged, and based on the imaging data, we can now make a better guess at the parameters for that patient. And the orangey colors are our updated guess. It's our updated belief in the parameters for patient 1. And so you can see there's still a lot of uncertainty, but the uncertainty, especially in some of the parameters where the measurements really tell the doctors a lot about what's going on, the blue is shrunk to the orange and reduced the uncertainty. And then if you can see the colors on the screen here, again, the blue band has shrunk to the orange band, still uncertainty, but a better idea about what's going on. And we could imagine doing that for all the patients. And if I go back and forth between these, one of the things I want you to notice is not only is there a ton of uncertainty, but look how different these patients are. Look how different the response is after the end of radiotherapy. And so what this tells you is there's so much potential value in a digital twin in the setting, because there's so much uncertainty and so much variability from person to person to person, that if you could start to personalize the treatment plans, you could really think about doing better. And these graphs here on the bottom show that. So these are Pareto plots that show the trade-off between the dosage, axis is cut off the bottom of the slide here, but this is the radiation dosage, and this axis measures the time to progression, the time it takes for the tumor cell count to come back up to a certain level. So higher is better, but lower radiation is better. So here's the standard of care, and what these lines show you is that with the patient-specific model, you could either delay the time to progression, delay the tumor cell count coming back up for the same dosage, or you could get the same performance and give less dosage to the patient, or you could improve on both. And again, you see the different trade-off curves done patient by patient by patient. Okay, and I should say this is just some initial work. We had actually the first paper on this just published last month, but it's such an exciting collaboration. We're actually also working with MD Anderson Cancer Center, also part of the University of Texas system, and really thinking about whether we can start to get these digital twin methodologies into the clinic and helping doctors to make better decisions. Really exciting. And I should say, as an aerospace engineer, I never imagined that I would ever be working on something medical, but this is the incredible story of computational science and mathematical modeling, is just the incredible range of applications that what we do can work on. So with that, I will close. I'm going to leave you with this chart, which is digital twins, truly a scientific grand challenge. And yes, it's very easy to get so excited about digital twins and what they could offer. It's also easy to open your email or pick up the newspaper and believe that digital twins already exist and that there are solutions out there for all kinds of digital twins. That is not the case. We have some great examples of digital twins that have been bringing value, but overall it is still, I believe, a scientific grand challenge, one that really needs to build on next generation mathematical modeling and computational science, and one that needs to bring all these different pieces together. AI and machine learning have a really important role to play, but also so do our physics-based models, our domain knowledge, uncertainty quantification, optimization and control, high-performance computing, edge computing, surrogate modeling, inverse problems, data simulations. And if there are any students here, I hope you recognize many of the topics that you get taught in an engineering and applied math curriculum, I think all really, really relevant for digital twins. So with that, let me stop. And if Pedro says so, we can take a couple questions. Thanks.
Thank you very much, Karen, for this inspiring talk. Many ideas, and so it's not surprising that you come from the reference center of these disciplines in the world. So is there any question? We can open the floor for a couple of questions, if there is any. Yes?
So what's...
Take the mic, otherwise we're not going to be recorded.
I'm not sure if anyone is related to this term, but we know intrusive reduced order models are the ones that got the physics on, and non-intrusive are basically the ones that rely more on data and does not pass through the physics. In the industry, how well accepted are the ones non-intrusive in general with respect to the intrusive one?
Yeah, this is a great question. So, like you said, the intrusive reduced models are the ones that really rely on the physics, and they're intrusive because they're derived from the high fidelity codes that encode the physics. And of course, them being intrusive means that sometimes they can be difficult to apply. Now, you said the non-intrusive ones don't encode the physics. I guess I would call those ones the black box methods, that really look only at the data and try to fit an input-output map. And that input-output map is maybe a generic statistical function. It might be a deep neural network. It might be a Gaussian process model. It may be a good old-fashioned regression model. But they don't have any explicit knowledge of the physics, but they're non-intrusive. So a couple questions, or a couple points to your question. One is, I do believe it's possible to do non-intrusive reduced order models that know something deeply about the physics. And in fact, this has been a huge focus in my research group for the last few years, that we're trying to be non-intrusive, just like the black box sampling methods, but we're trying to inherit the structure of the physics and really encode that in the reduced order model, which means my group's not allowed to use any neural networks, right? We are encoding the structure. So, but I think there's still many open questions. I think this is an important one direction, which is to say, how do you get non-intrusive methods that encode the physics? And by the way, by encode the physics, a loss function where you stick a residual of the physics, I don't think this is enough for the most important problems. It has to be a deeper encoding of structure. That's one direction. A second is maybe what you alluded to in your question, which is how well trusted are the black box methods? And the answer is, well, you know, it depends. Are people's lives at stake when you have to make your decisions? Is it okay to be wrong? You know, it really comes back to this validation, verification, uncertainty quantification. And unless you can do that in some way, then certainly when it comes to aircraft, civil engineering structures, and I think many medical applications, that's a no-go. But that doesn't mean the reduced model itself has to be validated. It could be validated in some other way as part of a bigger process, maybe using some kind of multi-fidelity method. So this is a great question. I think it's a really important, one of the important open directions that the community needs to take up, because we see these surrogate models out there that show incredible performance, but they only really work when you already knew what the answer was. And we need, as a community, we need to move beyond that. Yeah, it's a great question.
Is there any other question?
Thank you very much, Karen, for this talk. I am an associate professor here at the Department of Civil and Environmental Engineering, and I have one question which is a little bit more general, not related to the models previously, but when I make use of the answer you got from your question of the percentage of engineers here, 95%, right? I would say that in terms of civil engineering in this room, it's a high percentage as well, okay? So civil engineering is a field in which we are dealing with the built environment and the natural environment together, okay? And perhaps this real time is not that stringent. It's perhaps in some cases it's about years, the amount of measurements we do. But my question is, I would like to know your opinion for civil engineers. If you may go to the previous slide, there is one term here in yellow, data assimilation, which is how data from the real system is coming. So civil engineers, we have data from sensors, from point clouds, from images, and that's something that is not really present today in our schools. The schools, students are not really getting this education about how to measure the real world and putting this inside any model and any other colors you see here. So what about education? Do you have some ideas?
What about education? Oh, my goodness. Well, yeah, so you know, when we talk about modeling complex systems and trying to make optimal decisions, education is like the ultimate challenge out there, because as educators, we always want to add more to the curriculum, and it's a highly constrained problem. How do we teach, how do we prepare our students for the world they're going into? And I suspect in civil engineering, the discussions that you have are very similar to the discussions we have in aerospace engineering, which is our students now we have to teach them statistics and probability. We have to teach them computing. We want them to know machine learning. We want to make sure we cover ethics and societal responsibility. But by the way, they still have to learn fluids and structures and controls. And every time we sit around the table and we say we need to give something up, everybody argues and says, you cannot be an aerospace engineer if you haven't taken 2 years of, and then insert your favorite technical. So this is a real challenge. And I don't know honestly, what the right solution is. But there is no question that the students that have been educated today are going into a world where computer literacy is, I mean, it's not optional at all. And when we say computer literacy, I think right now, and I don't know about the curriculum in Spain, but where many US institutions are, we talk about programming, that's required. And then the students, of course, are choosing to take machine learning classes, because if they have machine learning classes on their resume, this is a door to getting an internship and maybe a job. And so they're choosing to take machine learning. But we don't enforce or even really talk, to your point, about things like inverse problems and data assimilation and even optimization. So I think these are all incredibly important parts. and somehow we have to figure out how to maybe get that ingested, get that included. Maybe just the last thing I'll say is, so I'm trained as an aerospace engineer. I think many of you here are civil engineers. We're all sort of very used to our disciplinary degrees. I think more than ever, there is such a need for interdisciplinary degrees, especially at the graduate level, that maybe at the undergraduate level, you know, of course we still need engineering degrees and mathematics and computer science, but at the graduate level, and this is what we do at the Oden Institute, our graduate program is called Computational Science, Engineering and Mathematics, CSEM, and it is a truly interdisciplinary degree where the students are required to take mathematics classes, and these are real mathematics classes. I look at them and I sometimes think I would not have made it through. They are forced to take computing classes, and this is Texas. We have TAC, the supercomputer center. This is real computing, and they must have an application, science or engineering or medicine. And you know, I think it's very grueling. But I think these kinds of programs that educate students across the boundaries, and whether that's through partnerships between engineering and mathematics and computing, or whether it's interdisciplinary programs, I think it's just so essential, because we do need people that will cover all of this. So I think it's a great question. At the undergraduate level, it's very, very difficult, but we have to take it on. But we cannot throw out the physics. The physics, it's on the top line for a reason, yes. Yes.
We're going to have one last question from Professor Papadragakis.
Very nice talk, Karen. Just to make a comment on the previous comment, that in civil engineering, in fact, there is a need for real-time answers in earthquake engineering and structural dynamics, when you can have the building in an earthquake, and then you have to control the passive or active control of the building or the structure. So there is a need for real-time answers in earthquake events.
That's right. And I think digital twins for smart cities is a huge topic of which civil engineers have a very large role to play in many aspects, actually, that require real-time or near real-time. Yeah, that's very good.
Okay, I think we have to close now. Thank you again, Karen, for this. And thank you all for coming.